Today, let's learn something about movement. And there are two types of movement. It's voluntary movement and involuntary movement. And have you ever marveled at the athleticism of a tennis player as she lands a perfect serve, or the virtuosity of a pianist whose fingers dance through a piece by Rachmaninoff? These are special and dramatic movements. Yet, in our daily lives, each of us performs a suite of complex, skilled movements that are equally remarkable. From walking and talking to saying our names or sending a text, we even use our muscles to reveal our current mood. A smile and a wave are universally understood. Movement is such an integral part of our day-to-day experience that we take for granted the sophisticated system that make these actions possible. The central nervous system, brain and spinal cord, directs the coordinate actions of the hundreds of muscles that enable us to move. These actions are refined and strengthened as we make our way through the world, adapting to changing circumstances and practicing, sometimes even improving our, our motor skills. And first, voluntary movement. To understand how the nerve system governs motion, we begin with the muscles, the structures of the body that produce movement. Most muscles attach to the skeleton and spine joints, the sites where two or more bones come together. The close relationship of these muscles to the skeleton gives them their name, skeletal muscles. Activating muscles can either flex or extend the joint that they span. Muscles that bend a joint, bringing the bones closer together, are called flexors. Muscles that straighten the joint, increasing the angle between the bones, are called extensors. Flexors and extensors work in opposition. So one set of muscles contracts, the other relaxes. For example, bending the elbow requires contraction of the biceps and relaxation of the triceps. For, for such motions, the muscles that promote the movement are called agonists, and those that op- oppose or inhibit the movement are antagonists. Skilled, rapid movements like throwing a dart are started by agonists and stopped by antagonists, allowing the lamp to accelerate and halt with great speed and precision. For some movements, agonists and their opposing antagonists contract at the same time, which is called co-contraction. This simultaneous action can stabilize or control a movement, such as holding an object at arm's length or stabilizing an immobile joint during isometric exercise. Whether flexion and extension, the movement of all skeletal muscles is controlled by the central nervous system. A skeletal muscle is made up of thousands of individual muscle cells, called muscle fibers. Each muscle fiber is controlled by a single alpha motor neurons. That originates in the spinal cord or the brain. However, each of these alpha motor neurons can control multiple muscle fibers. An alpha motor neurons plus all the muscle fibers is controls form a functional unit known as motor unit. The critical link between the central nervous system and skeletal muscles. When motor neurons die, as happens in disease like ALS, and people can lose their ability to move. And this picture shows the nerve system is divided in two. The central nerve system consists of the brain and spinal cord. The peripheral nerve system consists of nerves and small concentrations of gray matter called glia. The brain sends gray matter called ganglia. The brain sends message to the peripheral system, which controls the muscles and internal organs. And some muscles act not on joints but on soft tissue. And for example, muscles in the head and neck enable us to move our eyes, chew and swallow food, have conservations, and control our facial expressions. These muscles are also controlled by the central nervous system, and they operate in much the same way as those that attach to bones. And the second, involuntary movement. Many types of movements take place without our conscious control. Among the simplest and most fundamental types of involuntary movements are the reflexes. Reflexes are relatively stereotyped, automatic muscle responses to particular stimuli. Think of the rapid withdrawal of your hand after touching something hot. These reflexes involving the activation of sensory receptors in the skin, the joints, or even in the muscles themselves. The responses are rapid and occur without involvement of the brain or conscious attention. Instead, they depend on circuits of neurons located in or near the spinal cord itself. And in the left picture, it's one of the best-known reflexes called knee-jerk response. And the stretch reflex is seen at top of the image and occurs when a doctor taps a muscle tendon to test your reflexes. This activates muscle spindle sensory fibers, which send a barrage of impulses to the spinal cord, activating motor neurons and triggering muscle contraction. Flexation withdrawal, shown on the bottom of this image, occurs when you step on a sharp object and your leg is immediately lifted from the source of potential injury. The opposite leg responds with the increased extension so that you can maintain your balance, called crossed extension reflex. And back to the knee-jerk response, a stretch reflex that occurs when a physician strikes the tendon just below the knee with a small rubber hammer. This tap produces a slight stretch of the knee extensor muscle, which is sensed by receptors within the muscle called muscle splanders, which called muscle spindles. The spindles sense the extent and speed of the stretch, and stimulate sensory neurons, which send a barrage of impulses into the spinal cord. There are signals activate the alpha motor neurons that cause the stretched extensor muscle to contract, triggering the reflex. And in fact, the same sensor stimulus that directly activates the motor neurons controlling the extensors also indirectly inhibits the motor neurons controlling the antagonist flexor. This reciprocal inhi- inhi- inhibition is accomplished by connecting neurons that lie completely within the spinal cord. When these so-called inhibitory interneurons are activated by the original sensory stimulus, this send impulses that inhibit the motor neurons supplying the flexor. Thus, even the simplest of reflexes involve the synchronous activation of multiple sets of motor neurons controlling both agonist and antagonist muscles. And the muscle spindles mentioned earlier supply information about changes in muscle length or stretch. The brain in turn adjusts the sensitivity of the system where a separate set of motor neurons, gamma motor neurons, which keep the muscles spindles taut. Other specialized receptors called Golgi tendon organs locate where the muscle fibers connect to the tendon, detect how much force or tension is applied to a muscle during ongoing movement, increasing the movement precision. And these feedback systems are not unique to reflexes, but allow the brain to fine-tune how working muscles behave during a variety of movement tasks, from occurring walking, flying, swimming, or breathing. Central pattern generators, which evolved in primitive vertebrates and being studied to determine the degree to which spinal circuitry can be co-opted to recover basic posture and locomotor function after severe paralysis. And in the red picture, it showed a specialized cells called motor neurons and carry instructions from the brain along long axons that stretch from your spinal cord to the muscles in your head and feet. These cells can be the longest in your body, stretching the length of your leg to control the muscles in your feet.